Welcome, Alan Burnham. You have a BS in chemistry from Iowa State University and a PhD in physical chemistry from the University of Illinois at Urbana-Champaign. He spent most of his career at Lawrence Livermore National Laboratory and is currently a retired contractor there. He was also the Chief Technology Officer for American Shell Oil for 7 years and adjunct professors at Stanford University and the University of Utah for several years. His work has spanned many areas applied to energy and national security, including chemical kinetics, chemical reaction engineering, geochemistry, and material science. He has been a member of 10 professional organizations, including division-level offices in 2, and he has 300 published papers and reports, 2 books, and 11 patents. His awards include a Federal Laboratory Consortium Award for Excellence in Technology Transfer and an Outstanding Chemistry Alumni Award from Iowa State University. He is currently MRV Team Lead for the Climate Restoration Alliance OIF project. So here we go. Welcome, Alan Burnham.
Yeah. Yeah, thank you all. There's some scheduling challenges here. My talk at its core is about the interaction of science and engineering. It's my career, and essentially I'm a scientist by training, but my first project 55 years ago, which shows you how old I am, was to develop a new method for analytical chemistry to determine what kind of contaminants were giving the water in Ames, Iowa, a bad taste and odor problem. We increased the sensitivity of being able to do that by orders of magnitude and showed that what people thought was a problem, in fact, was not the problem. Right now, what I work on mentoring young professionals at Lawrence Livermore is how to develop chemical kinetic models that are actually useful to engineers, because scientists and engineers have a different perspective on things. So what you need to be able to do is develop algorithms that will work for engineers, but you understand them at greater detail so that you know what their scope of reliability is. And so that's really the kind of what I bring to this. And I've worked with Peter for the last 6 months. I'm new to this field. And the idea is, what is the right balance of science and engineering as we try to move forward? I can tell you as a scientist, it's fun to study science. I can tell you as an engineer, scientists will never solve the problem. It is really the interaction and symbiotic relationship between science and engineering that will get us down the road. So anyway, that's the nature of my talk. Some of the presentation materials are basically captures of other people's documents, which you don't need to look at. They're there for reference. I will talk about why that particular study is important. So next slide, please. I guess I have that, yes. So Lawrence Livermore, again, is the #1 supercomputer capital of the world with the El Capitan computer. But I can tell you, you don't need a supercomputer to know what kind of trouble we're in. There are people who say, well, we just solved the problem, we just don't use fossil energy anymore, and I can tell you that's not a good plan. It won't happen. I was born here, the little star there, you can see that, that was 75 years ago. And since then, population has tripled and energy usage is increased. And so if we say optimistically that we've reached peak global hydrocarbon emissions and we can ramp down at the same rate that we ramped up, we're only halfway through the increase in CO2. And that brings us to 570 parts per million. You go back in the geologic record, you can tell that's 3 to 4 degrees Celsius hotter. It doesn't take very sophisticated analysis to determine this. Okay, so the question is not, do we have a problem? The question is how we're going to solve the problem. And in my career, I'm not an activist. I'm not an idealist. I'm a practical problem solver. And so that's when I realized what we were up against and started hearing about what Peter says. I can help. I can help because I know how to solve problems. So one of the studies at Lawrence Livermore was following the California lead is we need to get to net zero by 2050. And so they spent a lot of time on that. But net zero isn't sufficient. What we really need to be doing is taking a couple trillion tons of CO2 out of the atmosphere. And if you look at the kinds of stuff that people talk about doing, it's not going to get us there. So what is going to get us there? So let me flip back now to the interaction of science and engineering. It's not one or the other. It has to be both working in parallel. By doing engineering scale-up experiments, you actually identify science problems, missing technology that you need to develop in a parallel track. And the majority, probably 80, 90% of your money is going to be spent on your process scale-up, but you will waste a lot of money if you don't actually have the supporting R&D to make sure you're getting it right. So that's why the bottom line here, parallel development of enabling technology and scientific knowledge is really essential for being successful in developing a process. All industrial processes go through what's called an industrial learning curve. This is one example. It's solar energy. You know, a long time ago, solar energy was a lot more expensive than you know, coal-fired power plants and all that sort of stuff. It's not really it's not true anymore, with the exception that a lot of people fail to realize that the cost of upgrading the electrical grid and the storage and all that sort of stuff also contributes, and the sun doesn't always shine, et cetera. So it's actually not as simple as oftentimes is portrayed in the public. But the idea is that you learn by doing. And there's also the other part of this is that scale is important in cost. Larger scale operations can deliver products at a lower cost. And so that's one of the things about the OIF that I'm going to be talking about. It looks like it can scale to large scale volumes, which will in fact be able to reduce costs. So this is an eye chart from Lawrence Livermore document. They were funded by DOE to look at, initially in California, how to reach net zero in 2050. And what they studied was all land-based options. When I said, well, what about ocean? I said, well, DOE is not interested in the ocean. They're only interested in what is in the contiguous United States. And so these are the topics of reforestation, carbon management, biochar, biomass gasification, et cetera, et cetera. And so to put the conclusion in a nutshell here is that most people think growing plants is the way to solve our climate problem. Well, when you look at how many plants you can grow, it's actually not. It's very inexpensive, and there's lots of benefits from growing trees and et cetera, but it does not scale to the volume of CO2 that we need to take out of the atmosphere. So gasifying bio waste, et cetera, is the next cheapest. Gasifying and then converting it to a liquid fuel for airplanes, that's next. But that still doesn't get you to net zero. So now you get into direct air capture, and that's expensive. And it's expensive even to reach net zero. If you're talking about drawing down CO2, it becomes not a solution. We're talking if we said, as a United States, we're going to go sequester our legacy emissions of 450 gigatons over 30 years, that's 15 gigatons per year, and at $200 a ton, that's $3 trillion per year. Now, predictions of the future are often difficult, but I can tell you with 99% certainty, we are not going to spend $3 trillion a year removing carbon from the United States budget. So that's kind of sets the stage of, well, where do we need to go? Well, lots of people have talked about marine carbon removal. And here's pictures from a couple of different documents. And they show you similar but sometimes different in detail kind of ideas. And they are all valuable. They will probably all contribute to some degree in what we need to do. They may have different costs and scalabilities, and that's fine. We need to be looking at all these things because at the end of the day, it's the market that kind of has to make sure that we've got the most cost-effective solution. What what I show now is actually a person from Woods Hole, Ken Bessler, was principal in this National Academy of Science study. It looked at various marine-based processes, and they highlighted 3 as being things that really needed a lot more study. At breakfast, I was talking to somebody who was working on seaweed cultivation. There's also the ocean alkalinity. There's lots of basalt around you can grind up and you can either use on land as soil amendment or you can put it in the ocean, et cetera, et cetera. But also there's ocean nutrient fertilization, and I'm sure there's plenty of the people in this room, if not in the conference, who know a lot more about oceanography than I do because I'm a physical chemist. I've worked on a lot of different things, but not oceanography. But the point here is that if you look at what they said, the cost of scale-up is low. The costs and challenges of counting how much you've actually accomplished is medium. And it's one of the most promising areas. There's still things we don't know about it, and we need to learn. But at the same time, it's something that they said could scale up for a cost of less than $50 a ton. But some of us think we can actually do substantially better than that. So here's another slide from one of their presentations. And there's 2 things I want to point out here. The third bullet there says potential to remove 0.1 to 1 gigaton per year, maybe more. And I guess I will assert that 0.1 to 1 gigaton a year is not sufficient. It does not really move the needle on where we need to go. So it's the maybe more that we need to find out. The other thing is the cost of less than $50 a ton of CO2, excluding monitoring and verification. And that brings up the second point, is that the current systems we have for monitoring and verification are too expensive. We need to work on the enabling technology to both improve our process monitoring while we're developing to optimize it, but also to make sure that other things are not going wrong, et cetera, et cetera. So I'll now switch to OIF, or ocean iron fertilization. And this is some from Peter's work, where he talked about the Mount Pinatubo volcanic eruption and the pause in the CO2. And he has calculated 20 gigatons removed for at least a few decades based on the shape of the curve. Now, I think there's still people debating as to whether or not you're right on this. And my position is not to say I'm absolutely sure that it was 20 gallon. The point is that it's large. We don't know how large, and we're not going to know how large it can be until we actually do at-scale experiments. And so that's what, in my view, needs to happen. So I am not an oceanographer, but I look in the literature, and I can do a calculation by other techniques, looking at the net productivity of the ocean and things like that, and I can come up with a number of, say, 4 gigatons per year. So maybe it's multiple gigatons per year, maybe it's multiple tens. I think the real answer is going to require us to get serious about scale up and really understand what we can do safely and productively. And so let's get back to this slide. Where are we and where do we need to go? We're at the very beginning of this. There have been some small-scale experiments which we've learned some things. In our organization, we're hoping to do a pilot scale at the end of 2026. So the question is, will we understand OIF perfectly before we do our pilot scale? I can assure you the answer is no. But I will also assert that without doing pilot scale, we won't even know all the questions that we need to answer. So it's the symbiotic relationship between doing larger scale experiments, finding out what you don't know, going back into the science. This is my career. In an experiment early in my career, this happened to be with oil shell retorting during the synthetic fuel heydays in the late 1970s. This company says, oh, well, we've discovered there's all this sulfur, and we have to be able to dissolve our sulfur cleanup system. And so can you figure out what the reactions are that are causing all this? So we went to the lab, and we did a whole bunch of experiments understanding why the sulfur was there and what kind of reactions it did and what that implication was for how you had to design your industrial process. And that's the kind of stuff that happens during large-scale industrial process development. So, so then the proposal then is to do an experiment in the Philippines, hopefully by the end of next year. You know, if the resources available, we can do it. It's shown here in the, well, I'm not even sure what color that is, chartreuse, I guess maybe. You know, the downwelling eddy there, and what Peter has brought to the table is saying, you know, the scientists, and rightly so, are worried about the sedimentation rate of the stuff that grows and how much of it actually gets deep enough to be permanently sequestered. Well, if you do this in a downwelling eddy, you have advection to help you with sedimentation, and so you can get a much higher storage efficiency. Now, we don't understand that in detail, but it's the kind of experiment that you need to do to be able to understand it in detail. I mean, Stokes' law, which is the law that governs sedimentation, you know, it's been known for, I don't know, 100 or more years. When I was working on laser fusion, we actually used Stokes' law to calculate the sedimentation rate of dust that's generated during a flash lamp that drives the laser. So you know, I'm familiar with that, I've used that. But the point is that there's a lot of complexity in the ocean that you can't really replicate in a true ocean experiment. So that's why you need this back and forth between the science and the engineering. So, MRV, multi-step process to measure the amount of greenhouse gases removed by a specific removal project and reported to an accredited third party. Well, okay, that sounds like a lawyer wrote that. In reality, there's two reasons for MRV. One is that if you're doing OIF, you have to know what you're doing. You have to, especially if you're trying to optimize your process. So you have to have feedback. This worked, this didn't work, et cetera, et cetera. Do I need to apply more nutrients, less? How fast do they disperse? All this sort of stuff. You know, it's just an engineering reality. You have to have diagnostics to understand whether or not your process is working and how to make it better. The other part is, and that's an inward-looking thing. The other thing is outward. You have to be able to show to other people that you actually know what you're doing, because there are things that can go wrong, and there's you know, the fear of the cowboy who's going to go out there and just spreading all sorts of stuff out there and making a disaster, et cetera, and that's the worst case scenario. But if you go to the other part, which is there eventually a carbon credit market for here, you have to have a way of saying, well, in fact, how much carbon have you been able to prove that you've removed? So there's lots of reasons to be able to do MRV. So one of the problems that we have right now, and this goes back to the National Academy, they said, oh, MRV is really expensive. Well, okay, I would agree with that. And so part of the enabling technology development we have to do is we have to make MRV cheaper. It's just simply that simple. There's lots of ways that it can be done, and we're really in the early stages, and we're looking at both surface, meaning either above or below the water, and satellites. And the typical oceanographic detector for some species is, you know, ballpark $10,000. That is not viable for an extensive array to monitor this experiment. We need to get these things down below $1,000. And so there has to be a program to do this. This is not science, this is engineering. But it's engineering in support, you know, it's small-scale engineering in support of a large-scale engineering objective. But we also need to be able to learn more from satellites, because the satellites can tell us lots of things if we know how to properly analyze the data. So here's a satellite, OCO2 trajectory. This is a complicated slide, but it's actually really pretty simple. There's this turquoise or aqua lines that show you how the satellite goes around, and it spaces a couple thousand miles on each time around. And then the second one down, you see those light streaks? That's the reflected sunlight. And they've positioned this satellite just at the optimum angle to get the most amount of light reflected from the ocean. And then they analyze how much light, light got absorbed as the sun went down and back up. And it harkens back to the work I was doing as a graduate student on esoteric things like pressure broadening of spectral lines and stuff like this. I mean, the JPL people did a great job on this. And then the bottom one, there's those little blue streaks, which is essentially the CO2 concentrations that they analyzed. Now, Peter had this idea, okay, if you multiply the wind velocity times the gradient CO2, it gives you the CO2 capture rate. And I don't know how many of you have had calculus, but it's a simple product of two differential things, and the units cancel out and it all works. And so he has a student over there at Stanford doing this calculation, and the big plot is what his student Aurelian has done, and you see the different color codes for the rate of CO2 change. So should I believe this? Okay, well, I was back and forth with Peter saying, convince me that I should really believe that you knew what you were doing, right? And so we went through an exchange, and so I'll show you two things. Number one, this is a figure that I grabbed off the internet of the net influx in and out. In the dark reddish area, that's an upwelling area, and CO2 is coming out, and sure enough, Peter's student found that was a positive change in CO2. Then there's also the downwelling eddy areas. Well, you go to that area and it's blue, saying that there's CO2 being taken out of the atmosphere there. So I will prove. So that is basically proof that Peter knew what he was doing. So let's go on to the. We're going to have both fixed, also dealing with 6 fixed sensors, but as I told you, the sensors are too expensive. So if you consider a pilot array of 5x5 buoys and then supplemented by a mobile platform doing more analyses, this is kind of an early concept for what a pilot would be. The question is, how accurate do they have to be in order for you to figure out what you need to figure out? And so I used this simple plot from a paper from Smeticek in 2012, and he showed for an OIF experiment there was a drop down of around 20-25 parts per million of CO2 where the fertilization occurred. So if you want to determine very accurately how much CO2 was captured, you need to be able to measure reliably changes on the order of a part per million of CO2. And so here's the one on the left-hand side basically shows the manifestation of the doing it from the product of the wind times the change, but you have to be able to determine the change in partial pressure to about a parts per million, and you can also do it from the difference in the water and the air. That's a bit more complicated system, but and I won't go through all the details there because there's not a whole lot of time and it's probably not the right audience. But what I wanted to show you here is that we took a sensor, we tried really inexpensive sensors, and they just weren't up to the task. We found an $800 sensor showing you on the left-hand slide how 2 of them track together. And on the right-hand side, that's the difference between the 2. And remember, we don't care so much about the absolute concentration, we care about the difference. And so we can get the difference down with a standard deviation around 1.3 parts per million. And so this is an order of magnitude cheaper than what the oceanographers do. pH is also an important issue, and this shows you the carbonate equilibrium system and how with atmospheric CO2 going up and more dissolving in the ocean, the pH is going down. That's not good for forms of life. So we've also learned how to package these things and show basically as you change the pH, you can get the partial pressure of CO2 to go up and down. And this is basically swimming pool chemistry here. This is not very esoteric. Any of you have a swimming pool, you've done these experiments. So we've gotten good results now with this inexpensive sensor to do water monitoring, and it doesn't go down to depth, but it gives us this interfacial measurement that we're interested in, and we're going into doing more solutions of differential equations and stuff like that, which you need to do if you're actually the engineer trying to make sure you've number one got good information and are analyzing it correctly. So we know how to do that. And we've taken our system out and we've conducted some engineering tests. And the boat captain says, okay, I'm going to take you out into a rough ocean and you're going to learn what it's really like out there in the ocean. And of course, we found some needed design improvements. And then we'll have to go through some more engineering qualification tests, and then we're going to look at seeing how well the buoys track going around in an eddy, et cetera. So what I'm showing you is some of the engineering scale-up things you have to do is a successive set of tests to qualify your equipment and your processes to make sure you're actually doing what you think you're doing and what you need to do. So we don't claim to be able to do everything. We view what we're doing as complementary to what the oceanographic community has done, the biochemical Argo system. It's very sophisticated. You can learn a lot, but it's also very expensive. One of those platforms in our area would be a great science experiment. So we can look at this as opening up our pilots to the scientific community. Say, hey, these are opportunities. This is a very standard practice, by the way, is saying, okay, we're doing this for an engineering, but we welcome scientists come in and conduct their own experiments to find out what they're experts in. So we have an aggressive scale-up schedule. It's of course dependent on resources, and a mini pilot, which is another engineering qualification in late 2025, early 26, and then a 25 buoy test in Philippines. So that's kind of where we're going. We're looking for collaborations to get cheaper sensor technology. It's my contention that if people can develop more inexpensive sensors, they will actually have a larger market share. Not very many people are going to buy a $10,000 sensor, but lots of people could buy a $1,000 sensor. And we're also looking for other institutions who would like to conduct the add-on experiments that I mentioned. So anyway, that completes my story about the interaction of science and engineering and how we need to approach a scale-up which is in the time scale that Peter has talked about. Thank you for your attention.